Georgina, can I get you to start with tell us your name, spell
By the
your
way,
name.
do you want me to look at Stu or the camera?
No, me.
You. Okay.
So, Georgina, if you tell us your name, spell your name, and give us your title.
Sure. My name's Georgina Long, GeorginaLong, and my title is Professor Georgina Long, Melanoma Institute Australia and the University of Sydney.
Beautifully done. Good afternoon.
Good afternoon.
I just want to start with why you got into science. What was the attraction of all the things that you could have done from, well, when you grew up? What science? Was there any moment that...
So, why science? There weren't really any specific moments. I mean, there are a few, but I think at a basic level, and this is what I tell my children, it was something I was naturally curious about, passionate about, and good at. And I think those are really important elements where you're going to spend your lifetime or short life doing things that you like and that you're good at. I was always drawn to curiosities about how the world worked, why. I enjoyed maths even as a young kid in primary school. So I think science was just a natural thing for me to put my effort and time into. I have a family of doctors and scientists, a sister who's an electrical engineer, mum and dad who were both doctors but scientific at their core. And so it was quite natural in our family to have dinner table conversations that were about the world around us and why. Lots of why this, why that. Hypothesizing, questioning, being curious was very much encouraged, and there were no wrong answers. It was a discussion. But the beauty of science is that you endeavor to try and explain things around you. It may not be perfectly correct, but you take the evidence you have to come up with an explanation for what you're seeing, and that can flex and change in time. But it's still quite objective. It's why is the sky blue? Why do plants often, not always, why are they green? And why do we see flowers from time to time? What's their goal? All of these things that are naturally around us, we discussed. We also discussed politics, religion, sex in a very sort of objective, scientific, why sort of way, or curious way, I should say. And there were no topics that were off the table. We could talk about anything. So I think growing up in that environment with 6 children, I was the 5th.
You've 5 siblings.
5 siblings.
And how many went into sciences?
How many went into sciences? We all did science at school. And I'm going to count now, actually 3 went solidly into science. I don't know what you'd refer to as architecture. That's a science. It's a 6-year degree. It's a lot of physics, but it's got a lot of creativity. But so does science. Science is very creative. In fact, even coming up with hypotheses about what you're observing, that's a creative step.
That's the point most people are going to miss. Can you go into that a bit more?
So there is a lot of creative thought when it comes to science. To take the leap from observing things around you or observing things that we may refer to as under the science of physics or chemistry, engineering, whatever the curiosity is, to take the step to come up with a hypothesis about why that observation exists is extraordinarily creative. And then to go about trying to prove it requires a lot of breadth of thought. And so that's why the top scientists, the people who are leading, pushing boundaries, are actually incredibly creative. And therefore, that's the link, I guess, to things like architecture and even art and other subjects that we don't classically think of scientific. But science is creative and it's challenging. really challenging, which is fun.
Where'd you grow up? Where'd you grow up? Sorry.
Where did I grow up? I grew up in quite a few different cities around the world. I was born in Sydney, Australia. When I was 4, we moved to Italy, my family and I, all 6 children. I was number 5 of the 6. I have a little brother who's 18 months younger than me. So we lived in Rome for 2 years. And then from Rome, we lived in the US for another year and a bit. And then we came back to Sydney. I then later, after completing my PhD, moved back to the States for a period of time. So I've lived in a few different places in my lifetime.
Why the run around when you were young?
So my parents are both very adventurous. They were quite forward-thinking for their time, very forward-thinking for their time. And so my father was an anaesthetist. Before I was born, they actually lived in many different cities. So before I was born, they lived in London for a couple of years. They had lived in the US for a couple of years, came back, had me and my little brother, and that was number 5 and 6. And then we went to Rome and then US again. So they were very adventurous people. What drove them to Rome was pure adventure. My father took on a job in the embassy because they thought it would be great to live in the city of Rome. My mother went to the Vatican to learn a lot of Italian and history. So they were just in the library there, which is incredible. So, and my father worked. So they're just purely adventurous people. In London, before I was born, my father was training there, again in the US training. The second trip to the US, he was training. My mother was in public health. She was always talking about impacting many people. How can you work in health to impact thousands? So we'd have many dinner table conversations about sanitation, vaccination programs. I know all about polio and what it was like for my parents to grow up with kids in their class and neighbours with polio, and the impact of polio and the eradication of polio in Australia and the eradication of smallpox. So these were discussions we had routinely. It was just part of life. I thought that was normal.
And it was for you.
It was for me. It definitely was for me to always see yourself in a bigger picture. You were only a small part of a much bigger picture.
Sorry, got me. But this, this is the 60s, right?
70s. Oh, my parents, before I was born, in the 60s, yeah. They were married in the 50s. They both did medicine. And then in the 60s, I was born in the 70s, me and my little brother. Yeah. So it was a great time, actually. I've been in touch with my chemistry teacher and had discussions with her about education in general. And she's taught over many decades, from the late 70s right up to, I think she retired in, she was saying 2014, around then, 2015. So she's had this massive, long career. She was very influential, and she did not realise it. Often teachers don't. But we were talking about when was a good time did she feel, for high school students and education in science particularly. And she chose actually the 80s. She said the curriculum was refined enough for goals, but not too cramped and not too restrictive to encourage creative thought. So in terms of the 60s, I think we were still starting to find our feet in terms of ideas and putting them into practice, but also including women in that as well. So, and still today, actually, we struggle with that.
Well, no, it's amazing because 25 professors later, they're all saying that's the best generation that came through and had the freeness of ideas to go up and didn't fall back into preconceived notions, and also have achieved them up. They don't like the new generations coming up. They might be old and grumpy. I don't know.
I think they may be old and grumpy because I think that's the human I've heard that story again and again and again. This younger generation, but every generation says that. So I don't know. I think we are all old and grumpy, maybe, but certainly the 80s, from a teacher's perspective, who's now very well retired, was a sense of joy in teaching in that decade because of the curriculum and the freedom. A nice balance, and that's what we need.
That's your wheelhouse. That's your area too. Your time was the 80s.
Yes, high school, that is. High school, yeah.
You okay with that?
Yes.
Okay.
I can talk more about those sorts of things, but I hope that, yeah.
Well, okay, where did you do your PhD? And what was it? What was your PhD?
So when I finished school, I loved the sciences, just really attracted to the sciences. Less the physical sciences, more chemistry and maths. And I had a natural proclivity for biology, although I'd never actually formally studied that in my later years in high school. So I tried to think about, very immature, finishing school, what would incorporate my love of English with science, and thought science law would help with that, which it really does not satisfy the English part of me. But different strokes for different folks, as we like to say. But I just loved the sciences, so dropped the law after second year to focus more wholly on science and did a double major in pure maths and chemistry. So after that, I did an honours year in chemistry and then a PhD in chemistry. At that time, I was thinking I'd like to do medicine. I'd like to apply what I know in science in a biological way. Those were the questions that I was drawn to. So as we were mature, we get more cognizant of what we're passionate about and what we're good at. And that's normal. That's normal for all humans. And so that's when I started to think more biologically about what I was doing. My PhD, in fact, was biological, although in chemistry, organic chemistry. I was looking at the mechanism of action of a drug called streptonigrin and how it bound to DNA. So a true chemist, small molecules in...
You're going to walk me through that a bit, I'm sorry.
So it's a drug that's not used. It was used for lymphoma in the 60s, or went through clinical trials. And I was interested in how it worked because it would release free radicals or oxygen-free radicals near DNA and splice it up. And so I was looking at how this small molecule drug bound to small parts of DNA. What was that binding that allowed it to get close to the DNA? That was my PhD. I used a lot of different techniques: mass spectroscopy, NMR, nuclear magnetic resonance. I would make structures synthesizing these molecules or analogues of this drug to see how they bound to DNA, and learned a lot of techniques in terms of organic chemistry.
Well, so how out of the box, what is this?
That was the sort of early to mid 1990s. And then went after that and did a Fulbright fellowship at Scripps Research Institute, which at that time had only just expanded. It's a very immunology institute, but it had just expanded to include a department of chemistry. And so I joined a research scientist called Reza Gadiri. He had a large...
How do you go back with Scripps? What's Scripps?
Scripps Research Institute is a US research institute located in La Jolla, California, which is just an hour and a half south. It's in San Diego, really, south of Los Angeles. It's world-renowned for its immunology research. In fact, I believe it has the highest number of Nobel laureates per researchers in the world. I can't check that fact. Jim Allison, who was the scientist that drove the discovery of a molecule called CTLA-4, a receptor and ligand binding on T cells, the receptor CTLA-4 on T cells, which is a brake. He discovered that, and that has become the foundation for immunotherapies we use in cancer now. He came from Scripps Research Institute. So that's where I went for my postdoc, my Fulbright postdoc, but for the chemistry.
You went for the chemistry instead for the
Well, I was very interested again in how to sharpen our skills on selective kill of cancer cells. And I was working on cyclic peptides and nanotubes.
Selective kills. This is getting really interesting for me now. Because immunology is a new science, really, isn't it?
Well, not really, actually. It was probably known as cell biology or in another guise, but if we look at the Nobel Prize winner for, or awarded the Nobel Prize for Medicine and Physiology, it was Macfarlane Barnett, who is an Australian New Zealander who worked in Australia, researched in Australia. And he was awarded that in 1960, I believe, for his work on immune tolerance. So why does our immune system not attack all our normal tissue? What are the brakes on the system to stop our own immune system attacking us, but does attack cancer, viruses, bacteria? So that was his sort of question. And that actually is the foundation for what Jim Allison then did in its scripts and beyond, actually, in looking at what are the brakes, what are the immune checkpoints that stop our immune cells from attacking self. So they're all interrelated. So as a science, I mean, if we go back to the 1800s, it was observed with Colley's, for example, Colley's serum, where a person infected with a bacteria, you can take their serum and use that to fight other illnesses, and particularly cancer. It was only observed in one patient, but it got people thinking about the body and its natural resource to fight off the nasties. That is bacteria, viruses, cancer.
And vaccines. So
In
how far back
vaccines,
are we going for cowpox and smallpox?
well, cowpox, yes. We're going back, right back to the 1800s, actually, for these concepts. So these early concepts, if we really, the concept that your body can mount its own immune response, back in those days, they would have referred to it as clearing of this evil thing. They didn't have the detailed knowledge yet. Cellular biology was, in its infancy. So those concepts have really got their foundations way back. And so immunology itself really is not that young at all. But as a science that we recognize, and certainly immuno-oncology, using the immune system to fight cancer, is relatively new. It's a few decades old, many decades old, but in terms of really leveraging the immune system to fight cancer, that, and being very successful in it, like really leveraging it, that's new. That's about 10 to 15 years old.
Which is nothing in the great scheme of things. It's not even a generation, is it?
No. It's been absolutely tremendous, the leaps and bounds within the last 10 to 15 years. And then we've got these wonderful other leaps and bounds. And it's funny, it's a crisis, I think, that faces humanity that allows these leaps to occur. So one of the big leaps was HIV, AIDS, in the 80s and 90s, really pushed science really forward in terms of cell biology and virology and the immune system. We all know...
Could you just work me through that? Okay, well, we're making a bit of a leap because we started with cowpox and smallpox and the first vaccines.
Yes.
So that's the infancy of immunology. So we're stumbling upon this because we never saw a milkmaid who got smallpox.
Yeah. And I'm sure it dates back to, 2000, BCE, like before the Egyptian times, the Roman times. I'm sure there was some medicinal approaches that were using the immune system, but they didn't understand it or recognize it. But talking about the evolution in the last 200, 300 years, really, it started again with observations and creative thinking. I mean, it's a beautiful example to see that, if you inject a human with a viral part taken from an animal, you may actually have cross immune activation that protects that human from smallpox or other infections. These sorts of concepts, very creative.
So that's the first step, was a vaccine, right?
Yeah, but they wouldn't have called it a vaccine. But these ideas that they can actually impact human health. And this evolves with these observations. And then we sort of start to become more organized about exploring the science as technologies developed throughout the 1900s. And then you have people like McFarlane, Burnett. Then you have HIV come. I'm just making these leaps and bounds. There's a lot in between this, but let's take...
But it's good. I mean, HIV, okay, breakthrough. Why?
Because all of a sudden it became a human imperative to understand this disease that was killing people slowly by lack of immune reaction from infections. So particularly at that time amongst gay men and IV drug users, and this was crossing into the full population. Some great programs like protected sex with condoms and IV needle exchange programs really protected Australia. We were very protected. But that understanding of the biology, what was AIDS? Remember, the observation is these young men are dying from infections that they can't overcome. Infections we usually would only see in very immunocompromised people. But these people are not those on transplant lists. They're not people who have diseases that are immunosuppressing them and they're getting these illnesses. This is what HIV was, with a long, years before they developed full-blown AIDS. What was going on? We have this observation. Why? That was the question. And though that forced the development of cell biology and virology techniques that really opened up a whole heap of great benefits for human health. And now HIV is not a death sentence. We don't see AIDS.
How did it open up? It's something, ideas that were not looked at before, we'll look at anything now.
Yeah, or ideas we haven't looked at, but also the creative way of working out the experiments to test hypotheses. And that is really important. So assays to look at T cells, to understand T cells, to understand the phenotype of a T cell. We're talking now the early 90s. That massive curiosity and questions and trying to then say, well, how do we do this? How do we prove this? PCR, when did that come around? The 80s. All these techniques.
What's a T cell?
Exactly. What is a T cell? Well, it's a phenotype, right? But now we know it expresses CD3, and then there's some that express CD4, and there are some that express different proteins, and they have different functions. And if you actually look now at high school biology curriculum for immunology, it is incredibly in-depth. Not even I, when I was doing medical school, had the depth of knowledge that our year 12 students learn about the immune system. This all is a little bit of incremental knowledge on incremental knowledge, new techniques, creative thought about experiments to test your hypothesis. Oh, I've got a hypothesis that this virus, it's infecting this type of cell, let's say. Well, let's phenotype this cell. Well, how do we phenotype? You go back a few decades.
Give an explain phenotype, please.
Well, what type of cell is it? What are the proteins it expresses it? What makes it do what it does? All those questions. How do you prove that? Oh my goodness, we don't have the right techniques. We're limited. And that's where the question is creative, but then to prove that and to invent techniques and experiments to look at that. CRISPR, PCR, all these techniques, someone invented them. Now mRNA. These are incredibly creative, but they happen on incremental changes, and then something evolves.
And they're so new. It's like pushing against the door and flying open. All this new stuff has come out in 20 years.
Yes, but it's actually been evolving over 200 years, and there will be more. And we will look back in 50 years and think, how did we do that in 2025? You mean you couldn't answer the question that these T cells are specific against that antigen in that person's body? You could not work that out in 2025? That's how it will be, for sure. Because,
Hindsight's 2020.
yeah, so we're always going to invent because we are creative. Humans are creative and will continue to be creative. So back to the idea of immunology and cancer, it's been around for a long time.
I was going to ask you how you got into cancer, so you're leading straight to the next point.
So I got into cancer, first of all, because I was always interested in biological systems. I was doing organic chemistry. I was supervised by a fantastic woman called Margaret Harding, and I particularly loved this project on how this drug bound to DNA. That attracted me. And then from there, I got even more interested in biological systems. And long before I actually did my chemistry PhD, I was thinking I'd always like to do more biological sciences. And then medicine made so much sense to me. It seemed so encompassing and so deep on every level, although, you know, not going down one type of science. Excuse me.
It's water, sneeze.
No, I'm good. Thank you.
Normally 3. Get ready for the
Yeah, I know, but we'll see. So, where was I up to? PhD. Medicine seemed all-encompassing.
I was actually going to say, you didn't just fall into it. It came over you over a period of time, medicine, or was it you driving? Was there a catalyst that made you go into medicine, or was it just
So I went and...
slow falling, built up critical mass, and then you said, that's the way I'm going?
So going into medicine, I quickly sort of knew, really. And I went and spoke to a lot of people in medicine. At the time when I was still doing chemistry, I was still in undergraduate. In fact, it was when I was after second year science law, when I wanted to drop the law. I went and saw a woman called Anne Sefton. This is before I met Margaret Harding, who later became my PhD supervisor. And she spoke about a graduate medical program. And she was passionate about it and how fantastic it would be because we'd be learning medicine in a new way and you love your science and clearly you're doing well in your science. And I said, yeah, I do. I love my maths and chemistry. And she said, well, think about continuing that and think about the graduate program. Because at that time I could have gone straight into medicine, straight with what I'd done. And I thought, yeah, I'll keep following my passion and what I'm good at. So I went and dropped the law because I didn't enjoy that. It wasn't for me. And that was a good example of something that was human-made. It was a construct that was human-made. Whereas I preferred the natural sciences, what's observed around me, rather than something that we've made. And so I dropped the law in favour of a double major. And then I was speaking to Anne Sefton at the same time, and we kept in touch, and she was telling me about the graduate medical program that would be opening soon. And so I just kept on my path that I was loving, thinking maybe I won't do it, maybe I will, but loving what I was doing. And then after my PhD, I knew then I really did want to do medicine and went and did a postdoc. Came back and started in the first intake of the graduate program at Sydney University as a 24-year-old, around then, yeah. Yeah, okay.
Leisure.
So the 80s,
A
yeah.
friend of mine was the
Architect.
who did Leisure.
So Norm, Life Be In It.
Yeah, and was that part of Norm? He won the Academy Award. They won it in '76.
Yeah, it might
I
be.
think it was Leisure became a David Deneen who turned into a wonderful commercials director. But it wasn't great. The '70s and '80s were.
Yeah, no, it was that they were great. The public health messages were great. But see, I think the thing about that time in the 80s and the 70s is most people got news or information in two ways. Read, television or radio, really. That was it. It was very directed. So you had a bit of a captive audience. So
It's so concentrated, especially even with television.
Yeah.
Advertising is discovered now. They don't know what to do because it's splintered so far.
Exactly. My parents bought us these T-shirts, which is so typical of my parents, which said "Kiss a non-smoker, enjoy the difference." I recall when I was really, really young, flying to Rome as a family. Yeah, I know, in the Australian Embassy, and my parents were always kicking up a fuss about the smoking. I don't know if any of you remember, right up to the 90s. I mean, it was like row 53 to whatever, I can't remember, with the smoking rows. And if you didn't sit in it, you just got all the smoke. It was disgusting. So they were always complaining about that, always, and how unhealthy it was, etc. So that was our upbringing. But I don't know how I got onto that. We were talking about something else before.
Just drifting. That's good fun.
So, I think we were talking about cancer,
But I was saying how you got into cancer, but
medicine.
also I'm thinking of your parents. I mean, let's
Yeah.
face it, cancer or the search for cancer and the search for a cure, you could really say it's post-World War II.
Cancer's post-World War II. Yes, absolutely.
So,
And we weren't curing that many advanced stage cancers then. It was only germ cell tumours that we really could cure, and a few lymphomas with chemotherapy right up until recently, actually. That's advanced stage. But now, in the last few decades, we've really honed our skills in terms of targeting as we understand more about cell biology based on these leaps forward during the HIV era. And so these things push us forward. mRNA is another huge leap forward, massive leap forward. Wonderful for medicine and science. So, and then I've mentioned before PCR and CRISPR and these techniques that build.
letters and numbers to half the people watching this.
Yeah. Well, they're all really important techniques that allowed us humans to discover more about why things happen. Once you know why, you can then try and find solutions. And so a simple one is, why is the globe warming? That's science. Why are the temperatures going up? Then you have techniques to look at why, and you try and find answers so that you can then put in solutions. So ice cores, these are basic things. I am not an expert in environmental medicine, environmental science at all. I'd love to be, because I'm passionate about it. But the questions drive the science, which drive the experiments, which drive new techniques, which give us answers, which allow us to find solutions. And the cycle goes on and on and on, whether it be environmental science, whether it be physics. How can we get a computer chip smaller and smaller and smaller and smaller to atomic size? That's the question. Well, why is that unstable? What do we need to do to make that stable, et cetera, et cetera? Then you understand why, you can come up with the solutions. And so medicine's the same way. Why are these young men, let's go back to HIV because it's a lovely example. Why are these young men dying of infections so quickly? So it seems. And the why was, well, it's HIV. So what's the solution? And now we have solutions. We have antiviral medications that can control this virus. Cancer. Why does this person have cancer? Sometimes we know, sometimes we don't. How does cancer divide? Why does it kill someone? How does it do that? Understanding the cell biology, using techniques that have been refined over many, many decades, including things like CRISPR and PCR that enable us to more quickly and efficiently investigate why cells do what they do. We can then answer some of those questions as to why this cancer is happening or why is it dividing, and try and target that and find solutions. And that's what we've done in melanoma, my area of research.
You joined that together really swiftly. Well done. You stopped me asking about 3 or 4 questions. Is that your intention?
Well, you were saying people listening wouldn't understand, so I wanted to get that whole
That's great. You did
evolution.
Really well, what is CRISPR? Really quickly.
Oh, CRISPR, I don't actually use it, but CRISPR's putting...
New, right? CRISPR's
Well,
like
not
10
that
years
new
old.
now. No, it's older than that actually, but it's where you can insert and remove genes out of the genome. And so you can test a hypothesis really easily. It's used much more broadly than that actually. We're even using these techniques now to try and treat genetic diseases like sickle cell anemia, for instance, which is a genetic disease where your red blood cells sickle and die, hemolyze. And so it's a genetic disorder. If you can change that gene or replace that gene or fix that gene, technically the disorder should go away, as an example. So these are all just different techniques, and there are thousands of them. So, for example, earlier this year, I was at an immuno-oncology conference, the science, the basic science part of the conference in where was it? Los Angeles, actually. And the techniques people are thinking about. So one of our biggest problems, I work in the space of immuno-oncology in melanoma. One of the problems we're trying to work out is we're making vaccines for people who actually have active melanoma, advanced melanoma. The idea is that if we can expose that human who has advanced melanoma to similar but novel proteins that are in their tumor, their individual tumor, we can mount an immune response that's more effective for them against their tumor. Now, when you're looking at the host, the person with the cancer, we can take T cells we can give a vaccine that we think is going to work by looking at these novel proteins, but then we can see if the tumor shrinks, right? Then we know it's working. However, we need surrogates because we're not there yet. We're not seeing the tumors shrink, but we've got to learn more about the vaccine and why it's not helping us eradicate the cancer. So what are the experiments we do to understand that? And so we take blood from the patient, for example, and we can get their T cells, which are their immune cells in their blood, and we can make little examples of the proteins we just put in the vaccine, and on the Petri dish, see if these T cells are activated when they come in contact with these little proteins that we put in the vaccine. And that would say, oh, look, at least we're activating the T cells. But what if we did it a different way? What if we took the host, the person with the cancer, don't give them a vaccine at first, we'll give them another treatment, but we take their blood as soon as they're diagnosed, and we see what T cells they've got in their blood or in their tumor, and work out exactly what the protein is that those T cells are active against. How do you do that when you have the tumor and the T cells and you're trying to find the actual little antigen or protein it's responding to? Now, you can do things and just say, oh, they're responding to the tumor, but I want to know the sequence of that protein. And then I want to know which ones are the most active for that immune system. And then I want to try that vaccine, for instance. So that's cutting edge immunology. We haven't got there yet. But at this conference in February, I can see that we're emerging with these technologies. It's getting there. People are being really creative about what to look at and how to try and get to the point where I can take your blood and say, yes, you have some activated T cells against your tumor. They're not overcoming it, but maybe if I give some of my immune drug with a vaccine against those specific proteins that your T cells are already a little bit activated against, we can get there faster. Those sorts of ideas. That's just some of the ideas that I'm working with Professor Helen Rizos and Dr. Inesh De Silva and Dr. Ishmael Vergara in the lab. And the whole team, actually, Dr. James Wilmot too. But these are the ideas, as a clinician, I'm constantly thinking about. And then in the lab, because I lead a lab at Sydney University, how do we get there? And we think tank together.
It's exciting. How do you get there? And what is cancer?
Cancer? Yeah. What is cancer? Cancer is the uncontrolled growth of your cells, uncontrolled and immortal, that form either in the blood or lumps in the body that then eventually can, not always, kill you.
And immunology attacks it.
And immuno-oncology or immunotherapy or the immune system, if you've got cancer growing, obviously your immune system has not recognized it as something to get rid of, but has recognized it as family and lets it flourish. My job is to try to switch the immune system to recognize cancer as foreign, as something to eradicate, like your immune system does with simple bacteria and viruses.
Okay, so wow. So the leap into cancer.
So cancer,
Your personal leap into cancer.
yeah, my personal leap into cancer was a bit of a practical one. I've mentioned before that I always grew up with this concept of make a difference. And for some reason, I've always had a feeling that life is short. Even as a kid, I don't know, not everyone shares this. So I know other adults have had this experience as a kid where you just cannot grapple with the forever or the universe, things that are just never ending, and grappling with life ending and then what is forever. These, I remember distinctly episodes probably around the age of sort of 9, 10, 8, 9, 10, 11, around then, being really struggling with those concepts. And I think it was with pets dying, really understanding death. And then my grandmother died around that same time. Two of my grandparents died before I was sort of cognizant. And so my grandmother, it was important she died. So important, the impact on me, really sad and impactful. And so I guess I've always known life is short or that it ends at some point. And therefore, the lessons around the dinner table, it's funny how kids' heads take these little bits of information and you have your own adult thoughts about things through your childhood. But it meant that I always had a push or feeling that I was running out of time, which is pretty not great, but that's how it feels. I'm running out of time. I've got to get things done. Life's short. And so when my mum and dad and my siblings would talk about things that impact many, we talked about architecture a lot. I have 2 architects in the family, for example. History, how history repeats itself, how human behaviour hasn't really changed over thousands of years, etc. All those sort of concepts. And then my mother's sort of mantra to make a difference to many. I was compelled to do things that would impact many in a collaborative way. I distinctly remember my mum talking about the joy of having one patient when she was back in the emergency department training again after she'd had some kids, saying that's very pleasurable, the impact of helping one person, but imagine the impact of impacting millions and thousands. And so I guess with that in the back of my head, not conscious of it, after then doing medicine with Anne Sefton's advice, another great woman, Margaret Harding, another great woman. I've had some wonderful people in my life, my mother and my father, of course. When I did medicine, I knew I wanted to be a physician. So a physician is the specialty of diagnosticians of, what's that television show? House. Yes.
Both went there.
He's a physician. So within that specialty of physicians, you have immunologists, hematologists, oncologists, cancer specialists, renal physicians, respiratory physicians, neurologists, cardiologists, gastroenterologists. They're the diagnosticians and the investigators. They get to the bottom of what's going on when other people don't know what's going on. As an oncologist, we work out, number one, is it cancer and what type of cancer it is and how we target it, for example. So I went into physician's training, and then when it came to decide on my specialty in medicine, remember I've come from a background of chemistry and a postdoc in chemistry, and that was hard. That script, it taught me to aim high. I didn't mention that, but that taught me if you're going to do anything, again, that whole impact thing that I had from my mother, I had with Reza Gadiri, and it was an absolute eye-opener for me. And it was, if you're going to do science, make sure it's worthy of the cover of Science or the cover of Nature. That was, and he got covers, by the way. He's had multiple publications that have been the cover of Nature, and I think Science too. So that was an eye-opener. So anyway, that just segued, yeah, these impactful people who had these concepts. But anyway, so now back to finishing my physician's training and then having to choose a specialty, I was actually in a quandary because at that time, we're talking sort of the mid-2000s, cancer really is a disease of the older person. And for oncologists, we treat cancer with drugs versus a surgical oncologist who treats cancer with the knife versus a radiation oncologist who treats cancer with ray beams, right? So the surgeon and the radiation oncologist just target one bit of cancer. They don't deal with the systemic nature of cancer, the fact that cancer cells get into the bloodstream and can plant their home around the body. That's what the drug doctor does. That's what the medical oncologist does. So I struggled because at that time, we were not curing many advanced cancers. We had not increased our cure rate much compared with when we were using chemotherapy back in the 70s and 80s, really. We had been successful as a field, medical oncology field, in using chemotherapy to mop up, that's called adjuvant, mop up cancer cells we couldn't see in early cancer. So people with early breast cancer, for example, by that stage when I was training, we'd give them a lot of chemo after the lump was removed from their breast. Now, they didn't have advanced cancer, they had early. And so they'd get a course of chemo, usually for 12 months. And that was when we were most successful. We'd prevent it from coming back. But we were not curing many advanced cancers, certainly not advanced breast cancer. And still today, it is actually hard to cure advanced breast cancers. That's breast cancer that spreads around the body. We're getting there with the subtype, with immunotherapy. Colorectal cancer, similar thing. We are not curing many advanced colorectal cancers. We're curing them early with adjuvant mop-up after the initial surgery of early colon cancer. So just the first lump in the colon may go to nearby lymph nodes and that's it, but not when it's distant spread. So melanoma was in the same boat. Death sentence. It was worse than pancreatic cancer is today, which is one of the worst cancers to get. It's the least curable, especially if it's advanced, it's incurable. And glioblastoma, that's primary brain cancer. So when I was thinking of my specialty, I was thinking, gosh, do you really want to make an impact to many? Again, it's my mother's words and Reza Ghadiri and, the whole sort of ethos, life's short, really make a difference. When everybody, or the people you can't cure, generally, not always, generally are older at the end of their lives and using things that may prolong life for a few months. That's it. Is that really what you want to do? So I struggled because I had a PhD and a postdoc and I was always interested in cancer from a scientific point of view, from a cell biology point of view. Watching people die of cancer was heart-wrenching. So it was really difficult. How am I going to impact this? And the science is fascinating, but the journey is horrific for people. In the end, I thought, I have to go into it because I've got all this knowledge and I've got this passion. I really didn't know how I was going to manage the death part of it. I'd come to terms with my own mortality. That helps when you have you've realized you're going to die and that's hard. So I went into it a little blind, but hopeful that I would find a way to make a massive difference. And I then did my training and it was pretty heart-wrenching. But in 2007, which was my last year of specialty training, I went to the big American Society of Clinical Oncology conference. That's the world premier cancer conference for oncologists, medical oncologists particularly.
Cannes Film Festival of Oncology.
It's the what, sorry?
Cannes Film Festival.
Yes,
Yeah.
yes, you got it. And, or more like the Oscars, I think, because the Cannes would be the European Society of Medical Oncology, right? And they're both very big meetings. There are two premier meetings for oncology. Those are the most massive ones. Anyway, in 2007, I went to that conference and I presented something on melanoma that I'd been doing as a medical student. So I didn't mention that, but as a medical student, I was interested in melanoma. And I remember sitting in a tiny little room listening to stuff about this CTLA4, which I mentioned before, James Allison. And there was not many people there. And I was blown away because they saw complete disappearance of cancer with this drug called ipilimumab and tremelimumab, and it was all first in humans. So no one was there, no one knew about it. Not everyone responded, but when they did well long term, but it was only first in humans still. And I went back to Sydney where I was training at that point. I moved around in the years I was training, advanced training. We went to almost every hospital in Sydney. I was at Liverpool Hospital at that point. I'd already been to Concord, Campbelltown and RPA because we moved around. And I said to the head of department, watch this space. I think I might have said immunotherapy is about to explode. You should have seen these first in human results and phase 2 results on this anti-CTLA4. They all ignored me and just went, oh, yeah, she's on her own thing. And I was saying, it's really exciting. Watch this space. That was Eugene Moylan, who's a wonderful medical oncologist. He's, I think, much older now, but he's still practicing. Anyway, I remember saying this to him and he went, oh, yeah, no, he was, listen. But anyway, so back to where I was, 2007, and I thought, okay, what am I going to do now? I've just finished my training. I was pregnant with my third child. She came in December 2007. And I then in 2008 thought about what I wanted to do and I wrote a grant. And I decided that I wanted to do research and I wanted to do it in melanoma. And why melanoma? Several reasons. Number one, it was Australia's cancer and everyone was dying within 6 to 12 months when they had advanced melanoma at that stage. We're talking 2007, end of 2007, early 2008. Number two, so we had a lot of it. So we had a lot of material, a lot of people to help, and a lot of understanding to do science with. Number two, it impacted old, it impacted young, it impacted men, and it impacted women, everybody. And number three, it was also preventable. And I had this idea that if you could do anything in melanoma, you must be able to impact the other cancers who had a lot of chemotherapy that extended life, because at that time, chemotherapy did not even extend life in melanoma. And I remember being struck by a poor man I saw with stage 4 advanced melanoma in hospital as a medical student. The nicest guy, so young. He was in his late 30s. He was jaundiced and yellow because his liver was full of melanoma. And he had lumps, so metastases in his liver, everywhere, lung, but you could see some of his metastases on the outside of his body, all these subcutaneous deposits as well. And I just remember thinking, this is just awful. We need to be doing more. Anyway, so I ended up going into melanoma when there was nothing. It was all just chemotherapy. I wrote a grant during the longest I took off maternity leave, 14 months. I did a locum for a friend at Campbelltown at the time for a few months, but otherwise was at home with 3 kids, 4 and under, and wrote a grant during that time and got that grant for the Cancer Institute New South Wales Fellowship.
So I'm going to have to leap in at this moment because time is ticking.
No,
Yes.
time's ticked. You have to be at a meeting.
Okay, I do, but that's
I was
okay.
gonna
Let's
ask
wrap
about
up.
Technology.
Okay.
Do you need to be there at 4:30?
I think I do.
Yeah,
Can I check my phone?
yeah, of course. Your EA, I think, has messaged you, and Jen's messaged me as well.
Okay. Oh gosh, it's BioNTech. Okay. Let me just finish quickly up if I can.
Lovely.
They'll have to wait
We've
a
got
few
time
more
for
minutes.
technology, that'd be great.
Okay, technology? Okay. Anyway, so I went into melanoma and have loved it. And a lot of things happened since I've gone into melanoma, really got into clinical trials, first in humans right up to what we call phase 3, where we prove things are better than the standard. And it's been a blast, a ball. I've loved it. I love my collaborations. I love the multidisciplinary nature of it, surgeons, radiation oncologists, dermatologists, pathologists, and medical oncologists. It's wonderful. And Melanoma Institute Australia really is a standout in terms of that multidisciplinary approach to cancer. So the big leaps and bounds that I've been a part of, and really we've led the field, I as a medical oncologist leading the drug development part with colleagues around the world who are medical oncologists, really exciting work by leveraging the immune system. Taking that CTLA-4 that I mentioned before for that ASCO meeting 2007, but using newer versions of what we call checkpoint inhibitors. So we inhibit the inhibitor on the immune cell to kill cancer. I now am focused on the third space. This is a term I've coined, which really explains beautifully to my colleagues and researchers where we in melanoma need to put our attention. So we've cured melanoma. That's the first space with what we call anti-PD-1 treatment, a single drug. It's about 35 to 40%. That's the first space. Well tolerated, activating the immune system against the cancer and killing it. Another 10 to 15% need 2 immune drugs, 2 checkpoints. We're curing another 10 to 15% with these combined checkpoint inhibitors, but they can be toxic. Then there's the third space. They still die quickly. And that's the focus, both in our lab, what we call translational research, understanding why these patients are resistant and what drugs will overcome their resistance. And concurrently, I run a beautiful trials team led by a woman called Maria Gonzalez. And Alex Menzies works with me, a great colleague and medical oncologist. And we do clinical trials in this space. That is our goal. In the lab, we have used all our multi-omics technology, so looking at every bit of the tumor and the host, to come up with a single test that uses proteins, DNA, RNA, clinical data to give you a single prediction as to whether you're going to be resistant to the first and second space, so we can enrich our clinical trials in this third space, both clinically for patients, but also the tissue goes back to the lab to see how we can overcome resistance for that third space. So that is my focus, that third space. And again, the multidisciplinary team nature, surgeons who cut out the tumors, the scientists who work, and we work together in the lab. I lead on the experiments with Helen Rizos and James Wilmont, Ishmael Vergara, Chuba Nagaidi, Dr. Inesh Silva, together, and many others, on how to work out the resistance mechanisms. Because we need new technologies. We need new ways of thinking about it. It's very complex. The immune system is extraordinarily complex. So that's where we're at right now in terms of our work in melanoma. And what we do in the third space in melanoma will 100% undoubtedly impact other cancers, because most other cancers don't respond as well to the first and second space drugs. I think we've got a lot more work to do in the second space drugs, using them in other cancers. They don't use them as well as they could. But what we learn, and we're curing some other cancers, like a few non-small cell lung cancer, a few triple negative breast, head and neck, bladder, all comes from melanoma, all of that. So what we do in the third space in melanoma will undoubtedly impact other cancers. And that's why I'm so passionate about that. So what we do in trials and what we do in the lab, and our multidisciplinary clinical team.
Could we film a song of that?
Yes, you could. You could come to the MDT if you wanted to. You just have to let us know ahead of time. That clinical meeting's on a Friday morning at 7 a.m. till 9 a.m. It is world renowned. We have a lot of visitors come regularly to see it. It is a perfect representation of multidisciplinary team care. Yep. And the lab, you can film the lab too.
ACRF next.
Yeah, it's 36 to you.
That's okay. One more minute. Do you want me to talk about the ACRF thing?
Yeah, just I
Okay.
guess what access to innovative technology does for
Yep.
your
Okay,
research.
I'll do that. Okay. So a really good example of this clinical research, translational research interface is what we're doing with Professor Helen Rizos, who is a member of MIA faculty as well. And so with the ACRF, we've got a wonderful program in cancer looking not only at discovery, so discovery of resistance mechanisms in drug therapy, that third space, discovery of toxicity and how we can ameliorate toxicity so we can treat patients for longer and get more cures. So that's discovery, but also clinical decision making. And so the ACRF with us,
The Australian Cancer Research Foundation.
the ACRF, the Australian Cancer Research Foundation, has helped fund a really important program to deliver best clinical care and decision-making in drug therapies in cancer. It encompasses 4 important machines. First of all, the bioprinter. Second of all, Cell Discoverer 7. Third of all, the lunar, what's the name of it? The lunar comet. And then the last one is the Blaze. What it does is initially we take patients' cancer cells, we dissociate them. That's a process in itself. That's our biobank at Melanoma Institute Australia do that. We do the 3D printing. We make slices of those. They then are looked at with the Cell Discoverer 7. And then we do like multiplex protein imaging using the Lunaphore. And then the Blaze is used for our mouse models to model some of the things we're seeing in human tissue. It is a wonderful, all-encompassing program of research that will make a difference to the research we're trying to do in that third space to cure more, not only of melanoma, but of cancer.
Wow, that's perfect.
Is that okay? Thank
Your
you.
brain, all those pieces of equipment. Which one's the pink shiny one? That's the only one.